Dear students, welcome to the next lecture of electrical measurement. So, this is our second lecture of this second unit. In the first lecture, we discussed some basics about the galvanometer. So, from this lecture, we will start about the electromechanical instruments. Okay. So, we have to discuss some of the electromechanical instruments, like the first one is the PMMC type instrument, which stands for permanent magnet moving coil type instrument. Okay. So, the first one is the PMMC type instrument. Then there can be moving iron type instruments. Okay. Then electrodynamometer type instruments, electrostatic type instrument, and thermal type instrument. Okay. So, all of the instruments, they have their separate construction, their way of operation. Okay. And each of them having their separate advantages or disadvantages, which we will discuss as we'll discuss the specific type of instrument. Now, of these type of electromechanical instrument which we have to study, this PMMC type can measure the DC values, that is the DC current or DC voltage. So, it can only measure DC values, it cannot measure the AC values. Okay. Rest of all the instruments, they can measure AC as well as DC quantities. So, this is the first difference which you must know about the different types of instrument. Okay. So, as we will just progress in this different type of instruments, and we will just discuss each of them one by one. So, first of all, we will start with the PMMC type, but before starting the PMMC type instruments, let us have some basics about deflecting type instruments. Okay. So, deflecting type instruments are actually those instruments which are based on the deflection of a pointer. Okay. So, we can say that a deflection type instrument will use a pointer that will move over a calibrated scale to indicate the measured quantity. Okay. So, the deflecting type instruments, they will use pointer to move over a scale to show or to indicate the measured quantity. Okay, because most of the instruments, they are deflecting type instrument, that is all of the instruments which we normally use in our day to day activities in laboratories, they are mostly deflecting type instruments. Okay, and they all use this pointer and scale type of arrangement to indicate the measured quantity. So, that is why we must know about the basics of the deflecting type instrument before starting to study the specific type of instruments. Okay. So, any type of deflecting instrument is there. So, there will be three different forces which operates in these type of instrument. In any electromechanical you can say mechanism, inside the instrument, there will be three forces. What are these three forces? One is called the deflecting force, the second one is called the controlling force, and the third one is called the damping force. Okay. So, these are three different types of forces which operates in the electromechanical mechanism. So, forces operating in electromechanical mechanism inside the instrument. Okay. Now, we will see that what is the meaning of this deflecting force, controlling force and damping force, and how these forces actually they operate in any instrument. Okay. So, now come to this figure. Now, this figure actually describes the deflecting force in a particular instrument. Let us suppose that this describes the deflecting force in the PMMC type instrument. Okay. So, actually what happens that the deflecting force will cause the pointer to move from its 0 position when the current flows. Okay. So, as is being shown in this figure also, that when a current flows in a moving coil which is just placed in between the poles of a permanent magnet. So, you can see here that this is the permanent magnet, that these are the poles, this north pole and this is south pole, and this is a coil which is being placed in between these two poles of the permanent magnet. So, what will happen that when current will flow in this moving coil, so the current actually sets up a magnetic field that interacts with the field of the permanent magnet. Okay. So, there is the field of the permanent magnet also, and when the current will flow, it will produce its own magnetic field. So, that magnetic field which when interact with the magnetic field of this permanent magnet, so resultant what will happen is that a force is exerted on the current carrying conductor which is situated in this magnetic field, and consequently we can say that a force is exerted on the coil turns. So, as being shown in this figure that as the force is exerted on the coil turns, so it will just cause the coil to rotate on its pivots. Okay. And the pointer is fixed to the coil. So, in this way we can say that the pointer will also move over the scale as the coil will rotate. Okay. So, this is actually being shown here also in this second figure, that let us suppose that this is the coil. Okay. And the pointer is actually attached with this coil. So, this is the pointer, this is the scale which you are seeing here. Okay. This is the scale which is present in the instrument. So, as soon as this coil rotates due to this mechanism which I just explained, so this movement of the coil will result in the movement of the pointer over this scale, and in this way you will get your measured value, whatever quantity you are measuring, you will just get it by the reading of this pointer over this scale. Okay. So, this figure actually describes the deflecting force which operates in an instrument. Okay. So, obviously, on one side of the coil the force is in upward direction, on second side of the coil the force is in downward direction. So, this is all you know. Okay. Now, come to the second type of force which is called the controlling force, or let us first discuss the damping force. Okay. We will discuss the controlling force later. Let us discuss first the damping force. Now damping force can be explained with the help of this figure. Now we are able to see here that let's suppose that this is the pointer, okay, and this figure describes the oscillation of the pointer about its final value, okay, about which it will have to settle ultimately. So it will first oscillate about that value. So the pointer and coil will tend to oscillate for some time before settling down at their final position, okay. So this damping force actually it comes into play when there is this oscillation of the pointer and the coil. The damping force will be is required actually to minimize or to damp out the oscillations, okay. So damping force is required to damp out, or you can say reduce or minimize, whatever you can call it, to damp out the oscillations or to reduce the oscillations or to minimize the oscillations, okay. So the oscillations which you are seeing here, okay, so this is being shown here with the help of pointer. Similar thing you can understand with the help of this graph also, that if let's suppose that this is the pointer position, so it will oscillate. So I have drawn this graph in the last lecture also, I think, and I just explained this, that how the oscillation is taking place about the mean position, okay. So the damping force is required to minimize the oscillation. So this damping force must be present only when the coil is in motion, okay. So therefore it must be generated by the rotation of the coil. So normally in PMMC type instrument, which we will discuss later on, the damping force is normally provided by eddy current. So in PMMC type, the this damping force is usually provided by eddy current. So that procedure or that method actually is called the eddy current damping. So we can say that in PMMC type instruments eddy current damping is present, okay, because the coil former or coil frame is constructed of aluminum, which you know is a non-magnetic conductor. So eddy currents are induced in the coil frame, okay, and then it set up a magnetic flux that opposes the coil motion, okay. So in this way it just damps out the oscillations of the coil, okay. So this is the uh, the damping force, okay. Now come to the controlling force. The third of the forces is called the controlling force. So controlling force normally in the PMMC type instrument is provided by the spiral type of springs, okay, spiral spring that was also shown in the previous slide, okay. So this is the type of spiral spring you are seeing here, that these are the spiral springs, okay. So in PMMC type instrument, the controlling force is provided by these spiral springs. So spring will retain the coil and pointer at their zero position when no current is flowing, okay. So this is the function of the controlling force, and when the current flows, the spring wind up as the coil rotates, and the force they exert on the coil increases, okay. So what I just told you, that as soon as the current will start flowing, the spring will wind up as the coil rotate, and as soon as this spring wind up, the force which they are exerting on the coil will increase, okay. So the coil and pointer will stop rotating when the controlling force becomes equal to the deflecting force. So this thing I also explained in last class as well, that at steady state position or at equilibrium, you can call it, the deflecting force will be equal to the controlling force. So the pointer will stop at that position when the controlling force will become equal to the deflecting force, okay. So this spring material actually must be non-magnetic to avoid any magnetic field influence on the controlling force. Okay, so this the springs must be non magnetic. Okay, okay, so these springs must be non magnetic, and sometimes the springs are also used to make the electrical connection to the coil. Okay, so they must have a low resistance as well. So normally the material which is used for making the springs is phosphor bronze. Okay, so you can also write it phosphor bronze type of material is used for making uh, the controlling springs. Now come to the method of supporting the moving system of the deflecting instrument or the deflection instrument. Okay, so there must be some supporting arrangement as well, okay, which is able to contain or which is able to support the moving system in any instrument. Okay, so these two figures describe that system. The first one uh, is called the jeweled bearing arrangement. Okay, so this is the jeweled bearing suspension, whereas the second figure describes the taut band suspension. Okay, so this is these are the two types of suspension, the jeweled bearing type of suspension and the taut band suspension. Okay, so in the jeweled bearing type of suspension, which is shown in this left figure, the pointed ends of the shafts or pivots, they are fastened to the coil, are inserted they are inserted into this cone shaped cuts. Okay, so you are seeing here these cone shaped cuts. Okay, so these pivots or the end of the shafts are called the end of these shafts are called pivots. Okay, so these pivots they are just being inserted into these jewel bearings. So what happens is this allows actually the coil to rotate freely, okay, with the least possible friction. So this is the main feature of these type of suspension. Okay, so whereas in the second method which you are seeing here, that is this taut band type of suspension, it is much tougher than this jeweled bearing type of suspension. Okay, so this second one is you can say it is much tougher or strong, you can say, as compared to this jeweled bearing type of suspension. Okay, so actually in this taut band type of suspension, two flat metal ribbons which are generally of phosphor bronze, they are held under tension by the springs to support the coil. Okay, and because of the springs, the metal ribbon behave like the rubber under the tension. So what happens is that the ribbons also exert a controlling force as they twist, and they can be used as electrical connections to the moving coil. Okay, so in this taut band type of suspension, there is less friction as compared to the jeweled bearing type of arrangement. Okay, and as I just told you that these type of suspensions, they are much tougher or much strong than the jeweled bearing type of arrangement. Okay, so it is possible that the jeweled bearing instrument, if it is dropped to a floor, okay, the bearing will be broken, but in case of taut band instrument, uh, it is unlikely to be affected by the similar kind of this fall. Okay, now come to the uh, PMMC type instrument, that is the permanent magnet moving coil type instrument. Okay, so this describes the construction of the PMMC type instruments. Okay, so this is also called the D'Arsenal instrument, okay, just after the name of the inventor. So the main parts you can say which are in its construction is the moving coil, is the permanent magnet, pointer, okay. So all these things are there. So the you can say that the coil is being placed in between these pole shoes of permanent magnet, okay. uh, so this is the main feature of the permanent magnet moving coil type instrument, that it is a permanent magnet, it contains a permanent magnet with two soft iron pole shoes which we are seeing here in this figure, okay. And then a cylindrical soft iron core is positioned between these shoes, so that only very narrow air gaps exist between the core and the faces of the pole shoes, okay. So this moving coil is being placed to move within these narrow air gaps, okay. So the reason of keeping these air gaps narrow or small is actually to have the strongest possible level of magnetic flux which is crossing the gaps, okay. So these all the things are visible from this figure which is showing the construction. So this is actually showing the construction of this PMMC type instrument. This second figure also shows the construction of this PMMC type instrument, okay. So all these things which I just explained before this slide, that the instrument will also have the controlling spring. So this is also being seen here, that spiral springs are being also attached to the moving coil, okay. So one end of the spring will be fastened to the pivoted coil and the other end will be connected to a zero position control, okay. So the main principle will be same as I just described for the deflecting force, okay, in the previous slide, in the starting slide, that whenever there is a current which will flow, so it will just exert a force on the coil. So as soon as the coil will rotate, the pointer will also move over the calibrated scale, okay. So this will remain same here. So the current actually in this coil of the PMMC instrument, it must flow in one particular direction to cause the pointer to move positively from the zero position over the scale, okay. Because when the current is reversed, the interaction of the magnetic flux from the coil with that of the permanent magnet causes the coil to rotate in the opposite direction, and the pointer is deflected to the left of 0. So actually the terminals of PMMC instrument, they are identified as plus and minus polarity to indicate the correct polarity for construction or connection, okay. uh, and the instrument is called a polarized instrument, okay. So this PMMC instrument, I also told in the beginning that it cannot be used to measure the AC quantities or alternating current, okay. So it can, therefore it can only measure the DC values, okay, because it cannot follow the pattern of the variation of the current, okay. So if there will be variation in current, it will move in both the directions. The pointer cannot follow the variation, that is why it can only measure the AC quantities, or I am sorry, it can only measure the DC quantities, it cannot measure the AC quantities. The torque equation for a PMMC type instrument will remain the same as I discussed in the last lecture for the galvanometer, okay, as this has the same principle, that is the deflecting torque, or TD, will be equal to this N B L D and I, where all these parameters have been explained in the last lecture, okay. So this will remain same here also, and this controlling torque will be equal to k theta, okay. So for final deflection, you can say for final deflection, the controlling force will be equal to the deflecting force. Okay, so this k theta is equal to this deflecting force, that is equal to GIG, where this can be taken as the constant g. Okay, so this will be GI, or theta will be equal to g by k times I. Or if you want to express current in terms of deflection, you can represent in this form. Okay, so you can say that the deflection is directly proportional to the current. So from this equation you can say that deflection is directly proportional to the current passing through this meter. So that is why these PMMC type instrument will have uniform scale. Okay, so if you see the scale of a PMMC type instrument, it will be having uniform markings. Okay, these type of instrument also have certain, you can say, errors or problems while operating. Okay, like the main sources of errors can be due to the weakening of permanent magnets, okay, or the weakening of springs, or the error may be due to the change of resistance of the moving coil. So change of resistance of moving coil. So all these can contribute to the errors in the readings. Okay, because generally what happens that magnets are affected by the aging effect, okay, by heat and vibration treatment. So the strength actually reduces. Okay, so weakening of permanent magnet can be one of the reasons of having the errors in these type of instruments. Similarly, there may be weakening of springs also. Okay, so with time it is possible that the springs weaken. Okay, so however, the effect of weakening of springs on the performance of instrument is opposite to the aging of magnet. Okay, because the weakening of the magnet will tend to decrease the deflection for a particular value of current, while the weakening of springs will tend to increase the deflection. Okay, because we have just discussed that springs are used to provide the controlling force. So if springs will weaken, so that force it will not able to provide fully, so that means the deflection will increase. Okay, whereas if magnets will weaken, it will have the effect on the deflecting force, so that means the deflection will decrease. So that is why we can say that the effect of weakening of magnet can be opposite to the weakening of spring. But overall, if we see the combined effect of weakening of springs and magnets, so if we consider a 1 degree increase of temperature, so the overall effect will be to increase the deflection, because it will reduce the strength of a spring by about 0.04%, and at the same time it will reduce the flux density in the air gap for about 0.02%. Okay, so the you can say the combined effect will be to increase the deflection. Okay, and the third type of source of error can be the change of resistance of moving coil. So because we know that the moving coil of the measuring instrument is usually wound with copper wire of having some temperature coefficient like 0.004 per degree Celsius. So when the moving coil is directly connected to the output terminals of the instrument, the indication of the instrument would decrease by 0.04% per degree rise in temperature. So that means that as soon as the temperature temperature changes, so the change in temperature will have the effect of the change of resistance of the moving coil. Okay, so in this way the resistance changes. So in coming lectures we will see that what are the remedies to just counter these type of error, like to just negate the change of resistance. Okay, uh, the advantage which these PMMC type instruments offer can be uh, like the low consumption of power. Okay, so one advantage is that it has a uniform scale, or the second advantage can be it has low power consumption. So this is one more advantage which it offers. Okay, and the operating forces, they are large on account of large flux densities. So this results actually in the errors with due to the low stray, or due to the stray magnetic fields are small. Okay, so because the operating forces are very large here in these PMMC type instrument due to the presence of permanent magnets, so the errors due to the stray magnetic fields are small. Okay, so these are certain uh, advantages with these type of instruments. So this is all in this lecture, and the next topic will be taken up in next lectures. Thank you very much.